The Drought Code, or DC, is the way that the Fire Weather Index system tracks the effects of long-term precipitation deficits on the fire environment. This presentation will highlight its place in the FWI system, outline the inputs and methods for estimating the DC each day, highlight some interpretations, and discuss issues related to tracking deficits through winters in these northern landscapes. The Drought Code is the last of the fuel moisture codes in the Fire Weather Index system. It represents a fuel with a 53-day or 1,250-hour time lag. The DC has its strongest influence on the buildup index when the DUF moisture codes are also high. Like the FFMC and DMC, the Drought Code, or DC, operates like a bookkeeping system. Beginning with yesterday's DC, the first question is whether enough rain fell to reduce its value. If there was enough precipitation, a rain code is produced and used instead of yesterday's DC. Whether there was rain or not, today's temperature and a monthly scaling factor are applied to determine how much drying occurred since yesterday. This drying factor is then applied to produce today's Drought Code. The DUF plug profile depicted here shows that the DC is the numerical rating for the moisture content of deep, compact organic layers, like those found in the northern forests that concern us. The scale here shows significant thresholds at 350, 400, and 450 found important in Alaska. The DC is actually very similar to the Keach-Byram Drought Index used in the southeastern U.S., though it produces values somewhat higher with a maximum of around 1,200 instead of 800. Its practical maximum generally is that 800 value, though. The DC is an indicator of ground fire problems in peat and muck soils. Firefighters have related it to the difficulty of their mop-up work. However, alone, it is not suited as an indicator of fire ignition, spread, or even extreme fire behavior. These four images show a fire in Alaska from ignition early in the season to a major growth event that occurred later in the year. The Mississippi fire near Delta Junction in Alaska ignited early in the season with an extreme FFMC but low DC. It grew little until later in the season when both current conditions, an extreme FFMC in the 90s, and the seasonal drought, extreme DCs in the upper 400s, promoted large fire growth, even in the green tundra in the lower right. This graph highlights the typical fire seasons on our northern landscapes. A spring season where fires are primarily wind-driven on still cool surface fuels and damp DUF layers. The DMC-driven period in Alaska comes late in June when long sunny days dry the surface and DUF fuels rapidly. While drought-driven conditions come later in the season when shorter days might otherwise limit fire potential. Notice how the periods of fire growth shown by the black dashed boxes are more related to elevated DMC than to DC. Once again, there is a direct conversion from DC to the moisture equivalent for the deep organic soil layer it represents. Notice that there are several conversions suggesting the wide range of seasonality and fuel bed conditions across the northern forests. The black dots in the graph represent field samples of fuel moisture from DUF plugs and the corresponding DC value at the nearest weather recording station. The scatter suggests that weather factors alone may not be able to track or predict fuel moisture at a particular location. Again, converting DC to the equivalent fuel moisture shows its weak relationship to the 1,000-hour fuel moistures produced by NFDRS. Because the Drought Code tracks long-term drying, users are asked to determine when drying in deep soil layers commence in the spring. Specific procedures are outlined for selecting the startup date and the starting DC value to account for drought carried over from the last season. These graphics show the effect of carrying last year's drought forward into the current season by elevating DC at the start. The graph in the upper left shows the DMC, which is unaffected by long-term drought. The graph in the upper right shows the effect of adding 460 points to the DC at the beginning of the 1988 season in Fairbanks, Alaska. Notice how the two lines begin to converge by the drought-driven stage in late summer. Though its effect is indirect, elevated starting DCs, called overwintering, had its strongest effect early in the season in 1988, raising BUI 20 to 30 points in May and early June. The FWI was similarly most affected in the spring. It's important to understand the effects of human intervention on the objective nature of these seasonal codes. In this case, the BUI was dramatically affected in the spring, as well as when the DMC was most elevated in July. In closing, firefighters can see visual indicators of long-term drought, such as premature yellowing of green vegetation. But DMC is not necessarily an important factor for fire ignition, spread, and intense burning. Abnormally high DC can indicate potential for holdover fire, mop-up problems, more severe fire effects, and greater smoke emission. Elevated DCs can influence fire behavior predictions through the BUI. Now that you've viewed the presentations on fuel moisture codes, FFMC, DMC, and DC, go on and view the discussions of the fire behavior indices, ISI, BUI, and FWI.